not that many people, but at least some show up, which is good. Welcome to the session, What the CRaC? Coordinated restore checkpoint on the Java virtual machine. Unfortunately, with the light, the projector is not very strong, so it might be a little bit problematic to read something. So I'm Gerrit Grunwald, working for Azul Systems as a developer advocate. And we have a booth here, so if you would like to know something or would like to talk to me, just come to our booth and I will be there, probably most of the time. And if you would like to have the slides, you can just take a snapshot of that one, and then you will find it on SlideShare. You can also search on SlideShare for What the CRaC. You will find the PDF there. All right. So Java is great, right? We have a vibrant community. Could be bigger here in Chicago. I was a little bit disappointed to see so few people here. I thought it's bigger, but seems to be something in the US at the moment. People don't go to in-person events anymore. So in Europe it's different, but at least we have a great community. And we have, sorry?
It's cold outside as well.
Oh, is that a reason? It's cold outside? Okay. So we have hundreds of Java user groups. There's also the CRaC here in Chicago, and I will give exactly this session in 2 weeks here in Chicago again at the CRaC. And we have thousands of free open source software projects, which is great. But the real star of the whole ecosystem is the Java virtual machine. Doesn't matter if you run Kotlin or JRuby or whatever, everything's running on the JVM, which is great. The question is, how does it work? It's really hard to read, isn't it? If you can't read anything, just let me know. So I have just a very simple introduction on how the JVM works, and it's just to give you an idea what all this CRaC stuff is all about. So if you start with a Java file, then you usually put that into the Java-C compiler, and then this spits out a class file which contains the cross-platform bytecode. And if you have a JVM on your system, then you can run this bytecode and execute your program. And then there is the so-called class loader, which takes this class file and then loads it into the JVM memory. And once it's in the JVM memory, then there's this other thing called the execution engine. And you see already that the execution engine contains not only one thing, it's a couple of things in there. And let's take a closer look. So we have the interpreter, then we have the C1 compiler, formerly known as the client compiler. The older people remember that. And then there is the C2 JIT compiler, which is the formerly known server compiler. And then we have the profile and the garbage collector. This is the execution engine mainly. And we will just focus on the first three parts. So if we take the code that is in the JVM memory now, then the first thing that happens, it gets into the interpreter, and the interpreter converts it into the CPU-specific instruction set, right? And the JVM is watching that and profiling that. And what it does, it calls method counts in this code, right? And once it reaches a specific threshold, it will take the code and forward it to the C1 compiler, right? And the C1 compiler, I told you, it's hard to read. It compiles the code very fast without a lot of optimizations. And the reason for that is, I told you already, it's the formerly known client compiler. If you have something like IntelliJ or NetBeans or Eclipse, this is Java. And if you double-click the icon, you would like to start it up as fast as possible, right? So that's the reason why this is the formerly known client compiler. It should be, startup should be fast. Compile fast, low optimization. So then again, the JVM is watching this compiled code, profiling it, and figuring out, is there hot code that is called more than once, maybe more than 1,000 times, 10,000 times, then it reaches another threshold, a number of calls of this hot code, and then takes the code and forwards it to the C2 compiler, including the profile information. The C2 compiler, formerly known as the server compiler, is high optimizing the code, and because of that, it takes longer to compile, right? It's not that fast as the C1, because in former times, if you run something like a monolith, then it doesn't matter if it takes a minute to optimize or 2, because once it's running, it ran for whatever, months, weeks, right? So that wasn't really a problem. So that was the reason why this compiler is really highly optimizing the code that it spits out. Okay, and this whole process is also called JIT compilation. And we have that since JDK, I think it came with JDK 7, and then you had to switch it on, and JDK 8 made it the default. So from JDK 8 on, we have C1 and C2 in the JVM. And we have different levels of execution between these different steps, like interpretation, C1, C2. And you see already that there is interpreted code is level 0, and then we have 3 levels for the C1 compiler, and then there's level 4, which is C2 compiler. The reason for these 3 different levels for C1 is you can imagine if you run something on a desktop machine with a client compiler, if you have the thing up and running, you don't need to profile it anymore, right? So you can just run it as fast as possible, no profiling. This would be level 1 in this case. If you need profile information, then you can use either C2, the level 2 or level 3. The default that is used in the current tiered compilation is this. If it's possible, then it will be interpreted code C1, including the profile information, and then level 4 for the C2 compiler. There are different transitions between these levels. It depends on all kinds of things, but this is the preferred way of doing it. Okay, so that leads me to this execution cycle. And this is in principle, we have the interpretation phase, which is the first step, which is slow, execution level 0. Then we have the profiling, that profiles the stuff, finding the hotspots, which is the reason for the hotspot compiler. Then this will go on to C1 compiler, low optimization, really fast, again profiling, then C2, and then we have this other thing, and that's so-called de-optimization, right? That can happen. You would like to avoid that at runtime because this has really performance hits, right? So and we come to that in a minute. De-optimization means if we have a code block like this, which is just an if-then clause, and we check if the value is greater than 0, and if this is the case, then the result equals 3. Otherwise, the result equals 0. That's the idea. And when we figure out with the profiler that most of the times the value is greater than 0, that means the result is always equals 3, then it optimizes the code and just say the value is always, the result is equals 3. Because most of the times it was like that. And this is guarded in the JVM. So that means it's still watching the value. And once it's, in this case, for example, equals or smaller than 0, so this is the default. But if the other case is true, like it's equals 0, then it has to take the code, the already optimized code, and just throw it over the wall and again do the interpretation, the C1 and the C2 for the whole block, because now suddenly both options are possible. This is de-optimization. So that means first the code will be optimized in a specific way, like for example, we have branch prediction. So that means the JVM figures out a way, oh, this is the most used way. We optimize the code in that direction. Suddenly the other way happens, and then it has to take the code, throw it away, and do the whole thing again. And you can imagine that if you have highly optimized code running, suddenly you have to do interpretation C1, C2 again, it's a performance hit, right? Okay, that's all great, but it takes time. It's not for free. And if we take a look at a JVM performance graph, which is here level 2 to 1, then we see these 3 different colors, like there's a yellow one in the lower left corner. This is typically interpretation. That's in the range of milliseconds, 100 milliseconds. Then we have the green phase, which is the C1 compiler and the profiling. And then the C2 is the blue one. And you see it, the code gets faster and faster, right? And usually when we talk about JVM startup, and this is a little bit tricky, JVM startup, the definition of that, it's not really clearly defined. So this is what we here see. It's usually garbage collector pauses. And these gaps that we see in the beginning, this is the optimization. You see it really, the code was fast and suddenly drops because it has to go again to interpretation C1, C2, and then again it gets faster. So and you can imagine that you would like to avoid that if possible, okay? And coming back to JVM startup, it depends. The first thing, if you just have a JVM and you have one class, just hello world, you will figure out it starts up like this. It's really fast, right? This is in principle the JVM. It has to load the class libraries and all that, compile it and so on. And then there's the class, that your main class, and you have just one method. There's nothing really to do. If you now load an application, a bigger one, then you can imagine it has to load all the classes, interpret the code, compile it, optimize it, C2 compilation, and so on. Takes more time. So in principle, when we talk about JVM startup, so if people say, oh, it's JVM starts up really slow, it really depends, right? It depends on what you are doing. Usually this is the application initialization plus the JVM startup. This is what we say, this is JVM startup, the time to first response of the application. Then there is something like JVM warm-up. That means if you run your application and then you hammer it with some workload, then the code can be optimized for your application. That means this is typically JVM warm-up. It can take longer, right? So you run it maybe for 5 minutes, for 10 minutes, it can be an hour, depends on your application. And then it's really high performant and optimized. So if you hear people saying, oh yeah, JVM starts up slow, it depends. You really have to define it more or better. If we now take this knowledge to the microservice environments, then that means first time you start it up, you have to do the JVM startup, which means it takes some time. Second time you start the service again, third time again, and so on, and that kind of sucks, right? Because if you run microservices and you scale up fast, then you suffer from the startup times, which is really not a good idea. So it would be much better if you can do something like warm it up once, second time you start it, it's just fast, right? Fully optimized code, that would be great. And so let's take a look at some solutions that might help to improve JVM startup time. First of all, there's class data sharing, right? Probably everybody heard about it? CDS? Yeah, maybe? Okay, so in principle what it is, there's app CDS and dynamic CDS. And it's in principle, we dump internal class representations into a file. And then this file is shared, this information, on each JVM star. That means you load classes. And instead of loading them all the time from the file, we just load them in a specific representation and store it in a file. The next time we have to load it, we directly take it from there, which is much faster. This is the main idea. This is default since JDK 12. So you probably use it if you're in JDK 17 without knowing it. Okay. But that also means there's no optimization or hotspot detection here, right? This is really class loading time. But this also counts to JVM startup. So we can reduce JVM startup by using that. You can gain up to 1 to 2 seconds startup time if you use CDS, and you can even tune it, right? So, and this is also not only possible for the class libraries, but also for the application classes. So you have to take a look at that. If you don't use it already, it might help starting up the JVM. And there's also a session, if you look for that, there's one guy from Romania who's going around and talking just about CDS. It's also interesting. Okay, and it happens here at the class loading time. It's not in the compiling and interpretation and all that, so right? This is really just before that. Okay, the second thing that you can do is ahead of time compilation. So who's using GraalVM here? Someone? But probably all of you heard about it, right? Native image, and it's the new big thing. It's so fast, it's so great. This is AOT. I think OpenJ9 also supports AOT. It was in OpenJDK, but it's removed from Oracle right now because they now have GraalVM. But I think in OpenJ9 it's possible to do that, right? It is, yeah. Okay, so why not use AOT? You don't have to interpret the bytecode, no analysis of hotspots, no runtime compilation of code, start at full speed straight away. GraalVM native image does that. So does that solve a problem? Well, not so fast. If you think about it, then AOT is by definition static. So if we talk about JIT, this is like compiling all the time, if you would like, right? The code here is compiled before it is run. So that means the compiler has no knowledge of how the code will actually run. Not if you just take plain AOT. Then you can do something like profile-guided optimization. In GraalVM, what they do, for example, they also have a JVM. They have a compiler. They run it the first time with the JIT and take a profile of the application and then apply this profile when they create the native image to make it fast. But then again, this is just a snapshot. That means if the application behavior changes during runtime, you can't really react on that. Where on the JIT you can, right? The code will be, it could be decompiled and recompiled again at runtime and optimized. So that's the big advantage. So if we take a look at the performance graph with AOT, then this is not hard numbers because it really depends on the application code. But you can say with plain AOT and nothing else, you can gain up to 60%, maybe 70% of the JIT. If you use PGO, you can get higher. You can get sometimes even reach the JIT It really depends. There's no golden rule. But in principle, you will never really reach the 100% of the JIT. But you can get close to it. It really depends on the application. And to do that, like I said, you have to run it once to create the profile, okay? So if we do a little comparison, and I'm sorry for the colors, because it's really hard to read, I guess. Well, this is white, that should work. It means that the AOT has a limited use of method inlining. For example, it can do it once in the beginning, but at runtime, you can't really do. Whether the JIT can use that aggressively. You can, for example, also use runtime bytecode generation in the JIT, which is not possible in AOT. And you can reflection, it is possible in GraalVM, but it's not that easy. It's really hard. Where in Java or in the JIT is really not a problem. And using speculative optimizations, this is like branch prediction at runtime, for example. It's really not possible in AOT, but you can do that in the JIT all the time. So that means the overall performance is typically lower when using an AOT approach than the JIT. But this also depends. There's no golden rule here. On the other hand, that means, oh, there's one more thing I forgot to mention. If you have the deployed environment with the AOT, that means with the native image here, it's different from the development environment. So I talked to people at a conference, and then someone told me they have test coverage like 90%. They run it in the IDE, run all the tests, everything's green. They compile it into a native image and run it in production and it fails. So that's really hard to debug these kind of things, because native code is not Java code. It's different, right? And this is the biggest drawback in my eyes. On the other hand, AOT, you have full speed from startup, right, where the JVM needs more time because of this startup phase. There's no overhead to compile code at runtime. And of course, the memory footprint is smaller because the AOT code, the native image, just compiles the stuff that's needed. It's an advantage and a disadvantage, because that means if you drag in a lot of resources and dependencies, the AOT needs to know all the classes to make it really work. Otherwise, it won't work, because you can't load stuff at runtime. It doesn't work in AOT. Okay, that means the biggest disadvantages of the JIT, it's more or less, it requires more time to start up, CPU overhead to compile code at runtime, and the memory footprint is typically, it's larger, because we need to compile code at runtime and profile, and at the same time, we have to run the code, right? Where in AOT, this is all done, you just run the code. So that's the big disadvantages. Okay, and then there's this chart I found this is from Thomas Wittinger. He's from the GraalVM team, and he put that in the spider chart. It's more or less the stuff that I told you. And the reduced max latency means this is a garbage collection, right? Because in the JIT, you can choose between different garbage collectors. You can tune the garbage collectors. When AOT, you can't really do that. This is not possible. Okay, so let me take a look at the different approach. Right? There is this project called CRaC, hard to read here. That means checkpoint restore in user space. And this is mainly, it's a Linux project. It's part of the kernel already since 3.11, which was around 2013. So it's not really a brand new project, it's an older one. The main idea was to freeze a running container or application and then checkpoint the state of this application or container to the disk, and then restore the container or application in the future from that saved state, right? This is the idea. And it's already integrated in OpenVZ, it's in Linux containers, in Docker, Podman, they all make use of CRaC, right? Or it's possible to use it there. Okay. It's mainly implemented in user space. Oh, and I said it's only on Linux. So that means if you would like to use CRaC, you need to use Linux. So is someone running here production server on Windows? Or Mac? Or Linux? Most of the people use Linux, right? But yeah, you laugh, because but I had that last week at a conference, and I was pretty much sure that nobody runs production servers on Windows, but they do. So then it doesn't work, right? This only works on Linux. Okay, the main goal is migration of containers for microservices, and it depends on the proc file system. And because there are also Linux systems, they don't use the proc file system. Then CRaC, I'm not sure, but I think it won't work there. And it can checkpoint lots of stuff, like it can checkpoint processes and threads, it can memory map files, shared memory, application memory, open files and FIFOs and pipes, sockets, inter-process communication channels, timers and signals, and it can rebuild a TCP connection from one side. So there's no really a need to have both sides, right? Which is, that's something specific to CRaC. There are other projects on Linux that do more or less the same, but we use CRaC because I think it's the most advanced one, right? Okay, but it also has some challenges. For example, if you would like, you have let's say you create a checkpoint on one machine, and then you would like to restore that on another machine. You can imagine that could be hard, right? First of all, there's architecture. Is this the same CPU architecture? x64, ARM64, do you have the same memory? What is with the hard drive? All these things you have to take into account. That means if you have really the same machines, it might work, but if not, then you run into trouble, right? That could happen. Then if you would like to start up multiple instances on one machine, you can imagine that because the PID, the process ID, which is unique in Linux, is also part of the snapshot. So you can't really restore multiple of these things on one machine. You can do that using Docker. This is possible, but if you're just on a plain machine, it's really hard to do. If you would like to do that on the JVM, then the JVM would assume it's continuing its task after the restore. And the JVM itself might not even be the problem, but your application might have open database connections, open sockets, open files. If you create a checkpoint using CRaC, it will shut it down, store the state, and if you restore it, your application continues running, and once you would like to connect to the database, for example, it's not there because there is no connection anymore. So these are the problems, right? So it's not that easy. You can't just take CRaC and create a snapshot of a running JVM. It probably won't work with the standard applications that we have. So that leads me to CRaC, which is the coordinated restore checkpoint. And the big advantage here is the coordinated, right? The idea is CRaC comes bundled with a JDK, so you get a specific JDK. It's not the standard one, it's the standard one plus CRaC and some other stuff. The heap is cleaned and compacted when we create a snapshot or a checkpoint, so that means the JVM is in a safe state. It's not the cluttered heap that will be saved, then it throws checkpoint exceptions. If you have files open or sockets or database connections and you didn't really close them, it will tell you there is a problem, you better take a look at that. And it comes with a pretty simple API. We come to that in a minute. And it can create checkpoints using either code or Jcommand. Right, so you can create a checkpoint in code. Sometimes that makes sense. Sometimes I personally prefer Jcommand. You have to do it from the outside. But the problem then is how to figure out when is the application fully optimized. Sounds easy, but it's not really, right? Because if you run an application, how do you know now all the compilation is done? Now it's good. So now I can really create the checkpoint. Right? This is stuff that you have to figure out. You can use it also from code, but we come to that in a second. And it uses a JVM save point mechanism, which is in principle the same that is used if you do a full stop the world garbage collection. Then the JVM will take care about stopping everything, putting it in a safe state, and then we can create the checkpoint here. Okay, so there is a project. It's called CRaC. It's an open JDK project. That means even if we as Azul working on that, we provided that to the open JDK. That means the version that you can download is not Azul Zulu, but it's just an Oracle Open JDK version, and we patched it with this CRaC support. And you can find it here, openjdk.org project CRaC. Okay, so that means I told you the big advantage is the coordination, and what it means is if you have a running application, then the JVM lets the application know, now I will create a checkpoint, right? And then in the future, when you restore it from that checkpoint, again, the JVM lets the application know, now you get being restored from the checkpoint. And this is important to know. The question might be why. I told you already, if you have open files, then somehow you need to close them. And this is the reason why we have these two things. To start it, we have this option -XX CRaC checkpoint 2 equals path. So you call the jar, the fat jar, for example, and then you just point it to a path. You pass this parameter to the JVM, and when we create the checkpoint, the JVM will store the files in this folder that you defined there, right? That's the idea. And if you restore it, you just say Java -XX CRaC restore from, and then equals and pointed to the same path. The idea is, for example, sometimes you have applications that will be used in different departments. So that means the same application, but the one department uses it in that way, the other department uses it in a totally different way. That means the code, the optimized code in the end could look different. It's not the same. You can create checkpoints for both of them, and then just by starting and pointing them to the different files in that folder, that's the idea. All right, so I told you already it has a very simple API, and in principle it's just one interface. It's called resource, and it has two methods, before checkpoint and after restore. So that means if you would like to use CRaC with the JDK that we provide, you have to change your code. Sounds terrible, but it's not really. Because in principle, you have to just to make sure, first of all, it will throw checkpoint exceptions. So that means if your code fails, it will tell you, well, in this class, there was something, you better implement the interface there, right? So then you implement the interface, and then you have these two methods. And in these two methods, you can react on before the checkpoint will be created. You can do something like closing resources. And if it will be restored, you go in after restore and just restore these connections to the database, for example. And usually you have something like a database manager or something like that where you just implement the interface and then you have to take care about that. Right. So that's the resource objects. Somehow the JVM needs to know which resources to call. So that means we have to register them somewhere. And this is the context, right? It's a context. And how do we get the context? There is in the core class is something like core.getGlobalContext. And then you can just take the context and register your resource in that context. That's the idea. So it's the idea like this. You have your class, you implement the interface, then you get the context and say, register this resource in the context. And you do that in all these resource files that you have. And you define the order. Because you can imagine you might have code that depends on each other. So that means you have a resource like the database, and the other resource will write to the database. That means the database has to be there first. So you define the order, how you register them, and then the context will take care about the order. So that means it maintains a list of all the resources, and when you call the before checkpoint methods, they will be called in the reverse order you registered them, which makes sense. You register A, B, C, and then you stop the JVM and you do C, B, A, right? To make sure they are in the right order. And when you restore it, it will be again A, B, C, to make sure it's in the same state as you started up. And then, yeah, I already mentioned that there's this method core.checkpointRestore. It's a little bit misleading because it doesn't really restore here. It just creates the checkpoint, right? And then it stopped the JVM. I think the OpenJ9 approach, you can continue running the JDK, the JVM. With this one, it will stop the JVM, right? So it will kill it. Okay, and already mentioned, you can also use Jcommand to create the checkpoint. Now I have a pretty simple example, and I just created some simple code. It's a scheduled thread, will be called every 5 seconds. It will call a loop, and in this loop, which runs from 1 to 100,000, it will create random numbers. And then it will just take the random number and forward it to this isPrime method. And in the isPrime method, the first thing it does, it checks, is the result of this calculation already in the cache? If it's in the cache, it returns directly the result, and that's fast. If it's not in the cache, it calculates if the number is a prime. If you have a large number, it takes longer, right? So pretty easy. We have the result, we store it in the cache, and then we return the result. So this way it takes longer. So that means, and to make it more realistic, the cache forgets stuff after some time. Because if you cache something, you don't want to keep that forever, right? At some time it should time out, and then you just clean it up. Okay, so that's the main idea for the demo. It's just to give you an idea how it works. And that means the first run is pretty slow because the cache is empty. It has to fill it up. Every number needs to be calculated, that it's not in the cache. Over time, the iterations, the number to take for this 100,000 checks should be faster, right? It should be faster and faster over time. So I did a little test with this app, and on another machine, it took 9 iterations to level out around 1. And you see this, it goes up and down because the cache will always, after 10 seconds, it will wipe out some stuff, then they will be added again, wipe out, and so on. That's the reason why it's going like this. And this is really just to give you an idea. If you run an application, first you need to initialize everything, you run it, it gets faster and faster, and at one point you reach this level where you say, oh, now it's fast enough, that's good. Okay, so what I do here, and it's really hard to see, I'm sorry, I have two shell windows on the left side and on the right side. And on the left side, I just start my jar file with this parameter and point it to the CRaC-files folder. And then I start it up, and it will show me, because I just added some outputs here, like I show the order how I registered the resources. In this demo, I don't even need to register resources. I just did that to give you an idea, to see the order, right? To make sure that it's correct. And then you see the first run took around 27 seconds. Because the cache was empty, it has to fill it up. And then second one, 10 seconds, 4 seconds, and so on. It gets faster and faster and faster over time because the cache will be filled up. And then at one point, come on, oh, it doesn't work anymore. At one point, I reach something like 17 milliseconds in this example. That's fast enough, so the cache is fast now, it's filled, it's fast. And then I create on the second window, I create the checkpoint by using jcommand CRaC4.jar and then just point it to the same. I just create jcommand CRaC4.jar jdk.checkpoint. That's the command to create the checkpoint. You could also use the PIT. You don't have to use the jar file with jcommand because you have the PIT in the app. You can ask for that, and you can also just say jcommand then the PIT jdk.checkpoint, and this will then happen. It will on the other window. You will see it will. I don't know if it's readable. It will first call the main class before checkpoint, then it will call the generic cache before checkpoint, and then it will kill the JVM. It creates a checkpoint, it kills it. So now we wait, right? We wait more than 10 seconds. I told you the cache will forget the values after 10 seconds. If they are older than 10 seconds, what I did, I store the value in the cache. And in these values, I also store the timestamp. It's a current epoch milliseconds. And then every time I call the cache, it will just check, oh, are there values that are older than 10 seconds, and wipe it out. So I restore it now using this command CRaC restore from. I pointed to the folder where I stored the files, and bam, it's directly fast. The cache is filled, it continues counting. The question is, how does it work? Because I told you the cache will forget that it was that the values are older than 10 seconds. It will wipe out. We waited for longer. Yes. Yes, it's in memory. It's just a class. It's a cache class where I just store the files. Like in principle, it's a hash map, right? Usually, it will be stored. The cache will be stored in the state because the whole JVM will be stored. So also the cache. If you restore it, the first time I call the cache, it will check all the values and it will say, oh, wait a minute, these values are older than 10 seconds and will wipe out the complete cache, right? What I did to make it work, and this is something of the points you have to really keep in mind, because the whole JVM will be stored, in the method of the cache, the before checkpoint, I just stored the current timestamp in the epoch milliseconds. I stored it in a variable. And in the restore checkpoint, I just created the delta and applied the delta to all values in the cache. And so I could make sure that every value in the cache is valid, right? Because then the next time it will be checked, it says, oh, okay, these values are not older than 10 seconds. That makes it fast. So that means if you have time-dependent data in your code, you really have to take care about that. It could also be state. Let's say you have an application where you store a business process, like a selling process. So you have these different states, and now you store it with a checkpoint, and then you restore. That means the state that you stored might not be valid anymore. So you have to make sure to handle that correctly. This is in your hands. So that means if you run stuff and you have, for example, session IDs that timed out, and you store them in some list or whatever, it will be part of the checkpoint. The next time you start it, and it will check against the stored values, all of the values will be timed out, right? So you have to keep that in mind. If you run into problems, think about, okay, there's something related to time, I have to take care about that. Okay, and then it continues running, and so on and so on. So, already told you, I created the checkpoint with the command jdk.checkpoint using jcommand. Could be the jar, could be the pit, whatever you call. Or you can use it from code with core.jdk checkpoint, core checkpoint restore, sorry. And like I said, the name is a little bit misleading, and even use it from code. You can imagine if you change the code, you run it to create the checkpoint, then you have to disable the code to make sure it won't create the checkpoint the next time you run it, right? You could also do something like, if the folder for the checkpoint is empty, then create the checkpoint. If it's not empty, then don't do it. So there are workarounds to use it from code, because sometimes people have specific code to warm up the JVM, right? If you have a trading application, then usually what they do is they stop it in the evening. When they restart it in the morning, they apply a lot of workload to the application to make sure everything's warmed up. If you have this kind of stuff, then you know exactly the point when it's warmed up. Then you can do it in code, right? If not, you use it with jcommand. And yeah, that leads me to the next point, is when to create the checkpoints. It's a little bit tricky. So what we do at the moment when we test stuff, there's this parameter, if you start the JVM, where you can use -XX column plus print compilation. It will really print out all the compile steps that it does. If you do that, first thing that will happen, you see in the shell, it's scrolling like hell. Over time, that gets slower and slower because the code gets more optimized, right? And then it's really slow. From time to time, you see, oh, it's compilation. Oh, another one. And then you say, okay, seems like everything's now compiled. Then you create the checkpoint, right? This is something that we do if we test stuff. Makes sense, right? But can take some time. Depends on how large the application is. But this is made for microservices. This is not made for application servers to stop them, because usually you don't have to restart them in seconds. Okay. The demo code, if you're interested, it's in my own repository at GitHub. If you would like to play around with that, you will find the JDK. I will provide the links. You can download the JDK, you can download the code, and then just run it, and it will directly run. So then you can play around with the code if you like. Okay, so I showed you the stuff that we created and the demo that I created, and it worked, of course, because I created it, and it worked fine. So the question is, how good is it really, right? We, of course, made tests with Spring Boot, for example, with Micronaut, with Quarkus, and then we also did some XML transform, and these are the time to first operation. In Spring Boot, it took around 3.9 seconds to the point first of operation. Micronaut around 1 second, Quarkus was 980 milliseconds, and then XML transform took around 4.3 seconds. This was on the standard OpenJDK. Then we used that with CRaC, and then this happened in the startup times. It's 38 milliseconds for Spring Boot. This is really fast. It's in the range of native image that GraalVM offers, right? With the advantage that still the code will be optimized if it changes, right? So it's just the JVM. There's nothing really specific here. The JVM doesn't even know that it was checkpointed really. It got restored, and for the JVM, it's just, oh, I'm keeping running forever. You might wonder why the times are pretty much in the same range, even if the original times have been very different. The reason for that is we just rely on I/O. We stored it to the disk. Now we restore everything from disk into memory. And disks are fast, memory is fast. The only difference here is if you have resources that you have to re-establish, like database connections, sockets and stuff like that, open files, that makes the difference. But even this is always mainly in the millisecond range. So that can really increase the startup time. Okay, so the summary. CRaC is a way to pause and restore JVM-based application, and it doesn't require a closed world like the native image in GraalVM. They need really to know everything. We don't need, right? Even if you, after the checkpoint, you load some other stuff dynamically, it will run, no problem. The benefit is a potentially extreme fast time to full performance level, and it eliminates the need to do all this identification of hotspots, compile methods, and recompile and de-optimizations, because we did all that in the beginning, before we created the checkpoint, right? That's all done. So now the code is optimized. We create the checkpoint when the code is highly optimized, so there's no need to really do the hotspot thing and all that. And with that, we have a really improved throughput from start, and it's an OpenJDK project, and at least it can also save some money. So you might ask yourself, okay, I get it that it's fast. How can that save money? Well, if you have something like you run in the cloud, you have some microservices and you scale it up in the cluster, usually this is what you see. If this is the CPU utilization on the y-axis and time on the x, then first you see this high peak of more than 100% here. And this is mainly because this is the JVM startup. At the same time, your application's already running. And that means we have interpretation and compilation overhead in the beginning. So that leads to the fact that companies tend to, if they really rely on fast startup, they tend to buy the high performance nodes, lots of CPU cores in the node to make it really as fast as possible. But this stuff is really expensive. If you run that, and once it's compiled, then usually you don't need that high number of nodes or CPU cores because then the code is optimized, right? So what we can do, we can create the checkpoint here after all that is done. And the next time we start from there. So there's no need to have this lots of cores in the nodes, right? So you can use cheaper nodes or even less nodes to run the same amount of stuff. Right? This is the main idea. So you can get rid of the startup time and the CPU overhead. Still, it has the higher memory footprint, of course. It's a JVM. So all the information, the JDK, all the demos that I showed you here with the Spring Boot, Micronaut, Quarkus, this is all available here. So if you would like to run it and test it on your own, you will find the instruction on how to run the demos and all that in github.com/CRaC. And you need a Linux x64, so it's the only operating system is Linux, and the only architecture is x64 at the moment, which is the majority of all the stuff that it's running in the cloud. So you can check it out there. And there's also a wiki on the OpenJDK page that has some more information. And now let me show you the stuff really running. I think we still have, we have some seconds left to just show it shortly, because it's interesting to see. So this is the same stuff that I showed you. I have two windows. On the left side, I started up. Instead of typing it, I just put it in a shell script. It takes now 27 seconds, and it will run like I said, it will calculate the numbers, check them for prime, put them in a cache, and do that every 5 seconds. That's the main idea. So it will take up for the first time like 27 seconds, and then it will be faster. And at one point, we then just simply create a checkpoint. So come on, go for it. And it's interesting because I run that on a Mac. It's an older one, an x64. I run it in a virtual machine. So that makes it really slow. If I run the same stuff on my M1 Mac, then it takes 1 second for the first run. And then it's directly in millisecond range. So it's good that this machine is slower, because then we see the benefit. So this is your application running. It takes some time to start up. We need to really warm everything up. Okay. And now we say, okay, now it's a little bit longer here. And this is because you saw we removed some stuff from the cache. That's the first time after 50 seconds, I just start the cache removing things, and then every 10 seconds it will check that. So that's the reason why the 12th run took longer. And now I just create the checkpoint from the other shell window. Here we go. It tells me the PID that was stopped, and then on the left side you see it created the checkpoint. It tells me where it stored the files, and then we just wait a couple of seconds, longer than 10, to make sure that we have this cache problem that I told you. And now the interesting part, we stopped at 15, it should continue with 16, right? It should be fast. We have been at 57 milliseconds, should be in the range, because it takes longer to really optimize it, so it might be a little bit different, but it should be in the range. So I restore it. Here we go. It's 41 milliseconds, it's already fast. The cache is filled, and then 5 seconds later, the next run, and it's fast already. So that means if I stop it now, restore again, we will again restore from 16. Here we go, 40 milliseconds. So you get the idea. If you create your application in a Docker container with the CRaC JDK, you create the checkpoint in the container. Then you can create an image from that, right? Which starts always from that checkpoint. Then you don't need to compile it and everything in the beginning. That's all done. It directly starts with a high optimized code, and it's fast. That's the main idea. So, and this is what we are aiming for. And the problem is at the moment that this is only available on Linux, so there's no Windows and no Mac support. We provide a library that makes it possible that if the JDK that you use has CRaC, it will use CRaC. If it doesn't have, it just gives you a dummy interface so that it won't break in the IDE. So you can code against CRaC without really using it. This is also available in the GitHub/CRaC repository. If you're interested in that, you'll find all the information there. And with that, I'm done. So if you have any questions, you can either do it now or you come to a booth and I will be there. So thanks for attending. Oh, and there's one more thing I would like to mention, because people ask that if we create these files, how big are they? And it is, you see it down there, it's 31 megabytes for this application. And you can imagine that if you run, for example, your JVM with a heap of 128 gigabytes, then of course the files will be bigger, right? We compact the heap, but the files will be bigger. That means the startup will be longer, but it will be faster than starting up from a cold JVM, right? So this is just to keep that in mind. You need some disk space, which usually is not a big problem. But you can imagine if you run a microservice, you would like to keep the node as small as possible. You have to keep in mind, if you create the checkpoint, it takes some memory on the hard drive. All right, that's it. So if you have questions, you can ask me now. Or otherwise, like I said, you can just come to a booth and then I will be there. There we have more time because people will come here for the next session. Okay.